Hi. Hello, everyone. So I'm going to talk about this joint project with Alessandro Ilaci, who must be in the room, and Anna van den Wingern. It was kind of a fun project to me because it's definitely more their area of expertise than mine. So this is really a combinatorial work. So I'll keep the representation theory part to the second part. So we'll look at this mysterious symmetric function with some mysterious operators. So this is, I'll never really define it, these operators, but just know it's a symmetric function in this indeterminate xi with coefficients that are that will turn actually to be polynomials in Q. And the motivation that's written here is about, let's say in 15 to 20 minutes, I'll explain what this symmetric function is supposed to mean. Okay, conjecturally is supposed to be a certain graded Frobenius characteristic. But for the first part of the talk, let's say 2/3 maybe, I want to do combinatorics. So what we did mainly in this work is to give a combinatorial expansion. So we see the theorem on the left-hand side. So you have this symmetric function, and then you expand basically into monomials, okay? With some parameters, so the Q, you have an extra Q parameter. So what the sum is over so-called segmented Smirnov words, defined in the next slide, with certain descents and rises, and a certain statistic that we decided to call, it's called Sminversions. And then, as I said, in the second part, I'll explain where the symmetric function comes from and this whole story about the delta conjectures and the different covariance spaces. Okay, but for the first part, it will be supposed to be easy enough, just combinatorics, and we try to prove this theorem, admitting some stuff about the symmetric functions. Okay. So what's a Smirnov word? Just a word where the adjacent letters are distinct, okay? The alphabet is the positive integers. So for instance, here you have like a Smirnov words, you see that you have no equal adjacent letters. The length is the number of letters. And what's nice is that you can, as for permutations, you can define ascents and descents, okay, because you don't have equal stuff. So any position before n is either an ascent or a descent. Okay. So Smirnov words occur, for instance, if you, let's say, you must have seen them somewhere. Like if you take a word and you can actually, if you take the same letter and replace by just one letter, adjacent letters, I mean, you get a Smirnov word. Or if you, let's say, take the colorings of the path graph, then it's essentially a Smirnov word, this kind of stuff. So maybe you don't know the term, but you've seen them somewhere. Okay, so we actually want to do segmented Smirnov words. Okay, probably I'll forget to say segmented sometimes, but all the words we look at segmented, so this is just a concatenation of Smirnov words, basically. And you fix the shape. So alpha would be a composition there, so like a sequence of positive integers summing to the length n, and each wi is a Smirnov word. So the key is that between two Smirnov words, you don't ask for this, the fact that the letters are distinct. As you can see in this small example, you have a 2 and you have a 2 that starts the next one, okay? And you talk about descents and ascents only inside the block. So for instance, in this word, position 1 will be an ascent, position 3 is neither an ascent or a descent, okay? And then position 3 is an ascent, descent, etc., okay? So every time you have a block separator, you don't have neither ascent or descent. Okay, that's the main object in this talk. So if you have questions, now is the time. So we just define this set of all the segmented Smirnov words of a given length with the given number of descents and ascents. It's very easy to see that the number of blocks, the number of segments, if you prefer, is exactly n minus k minus l. So this determines the number of blocks. Okay, so this is the set, and we had this statistic. So I'll give the definition, but I don't want you to look at it too much. It's some sort of patterns in a word, okay? So it's basically, you have I smaller than g is a Smirnversion if it's already an inversion plus some extra stuff, okay? Just the important special case that I will mention later is if the word W It's what I call a segmented permutation. So it's a special case of Smirnov words where you only take letters 1 to n in the length n, right? And you just, it's basically a permutation where you created some blocks inside. In this case, it's easy to see that only the first two cases occur because in the cases 3 and 4 you have equalities. And then you can see that to get a feel of what these smear inventions are, they're just 2-3-1 pattern occurrences. I guess half of you maybe are familiar with pattern occurrences, plus the number of inversions where the occurrence of J, let's say, would be initial. Let's say initial, I mean the first position in the block. So it's some sort of mix of inversions and 2-3-1 patterns, and then generalized to words and not just permutation. Anyway, it exists. That's the important fact, that there is such a statistic. Okay, so just another definition. So we want to refine now, because of the theorem, we want to refine this with a certain mu. So mu is sometimes called like a weak composition, just a sequence of non-negative integers. And we define this set Smirnov of mu KL, just if you just select the words that have mu I occurrences of the letter I for each I, okay? And then from this, create the important thing is this generating, so that's a finite set now, okay? Smirnov words infinite, now it's a finite set. So this is a polynomial, okay? Just take the generating polynomial according to this Sminversion statistic. That's the one we want to show. We want now, okay? That's the main definition. And now I'll show you some combinatorics. So to prove the theorem, we'll actually want to prove a recurrence relation on this. Okay. So I should say that everything I say is totally not the chronological order of things or whatever. So I just mix. So it's like the hard thing, I would say, in this part was coming up with the notion of segmented Smirnov words and not really the recurrence. No. You can all prove the next fact. No. So it looks ugly, but anyway. So this is the main recurrence. So what do you have here? So I define this mir q mu kl. So I have to define this mu minus. So you just take the last part. So I assume here that mu m would be positive, and then you just remove mu m. Okay. So you're looking at the recurrence between words with a content mu, and then content mu minus means that the largest value has been deleted somehow. Okay. You don't want the value m. You don't want it occurring in mu minus. So that's an actual recurrence, as you can see, because the mu minus is supposed to be smaller. And what's nice about this, so it's very nice from a combinatorial point of view. Everything is positive here. It's actually even positive integers, okay? So these are the Q binomials. So I expect most of you know, it's just some Q deformation of the binomials. And you see all of these factors are actually just polynomials in Q with positive coefficients. So this is a very positive stuff. So you would like a combinatorial proof of this. And that's what we do in this work. I just show you the standard case. And then if you have time, one of these days, you can either look at the article and try to guess how to do the general case. So the standard case is this case of segmented permutations. I mean, you have one occurrence of 1, one occurrence of 2, up to one occurrence of n. Okay, just each letter between 1 and n occurs once. And then this recurrence simplifies amazingly. So it's just this tiny thing, which looks even more symmetric. Okay, just have one factor, which is this Q integer. Okay, that's the sum of powers of Q, and then you have something that looks very symmetric on the end here, okay? So how do you prove this? Just, okay, you take a segmented permutation of length n-1, and you want to insert n and see what happens, okay? So there are 4 ways this can happen, basically. Either you have 2 adjacent blocks with a block separator, and you put n instead of this block separator, so you merge 2 blocks. And then n would occur in the middle of a block, or you put n on the left of a block, or you put n on the right of a block, or you create a singleton block with just n. So, okay, these are the 4 distinct ways to do this. In general, for each of these cases, there would be B ways where B is this n minus k minus L, which is the number of blocks of the ending permutation. So that's why you would have this factor here, okay? These are the 4 terms that correspond to these 4 ways, and this is the thing. And then you check the power of Q, and you actually see that it behaves perfectly. So people who know this construction is well known in the let's say, the enumerative combinatorics literature. It's essentially the Laguerre history ways of building permutation, if you know. So just a word, if you want to do the general case, you wouldn't have to insert just one value, okay? You have to insert the value m, but you can insert them. Basically, you have all these distinct ways. They still occur, but with multiplicities, and they can all occur at the same time. So that's why you have these 4 big Q-binomial coefficients that tell you where to put m as a block separator, beginning of a block, etc. But if you know what you have to prove, if you have this, basically, I think you can all do it. Just have to be a bit careful of the way to do it. Okay, so we have this nice recurrence for the Smirnov, the segmented Smirnov words. It turns out that this mysterious generating function, if you extract the coefficient of x to the mu, you also have the exact. This was the starting point, I should say. This satisfies exactly the same recursion. Okay, and the proof was done in an article of Michele D'Adelio, who's in the room, and Mariano Romero, I think, is also there. Plus just some simplifications because they have a more general case and you just specialize at t = 0. So these were the 2 sides of this theorem there, just the coefficients of x to the mu. So you show that the coefficients on both sides satisfy the same recurrence, check the initial conditions, and you're good. So that's how you prove this theorem, that this symmetric function is equal, has this combinatorial expansion, okay? So that's what you have to remember. Now you can forget all about Smirnov words even. So I'm going to unless you have some questions now, and I'll go to the second part about more the covariant spaces. Okay, so where does this come from? So as I said, I'm not a specialist, but for me, so that's in this different covariant spaces stuff. What people do in general, so I mean, that's the fact that what people do. So we have some, more generally, a finite dimensional representation of Sn, okay? And then you have this magical Frobenius map, like this morphism that sends you your representation to a certain symmetric function, okay? It's even more than this because the Frobenius characteristic sends the irreducible representation V lambda to S lambda, so you get actually a short positive symmetric function here, okay? So that's what I note here by FFV, okay? And this symmetric function encodes up to isomorphism, it encodes entirely this representation. So it's a nice way to code a representation up to isomorphism. And then, since it's short positive, you know it's monomial positive, so it should have, if you have nice combinatorics in your representation, somehow you can hope for a combinatorial expansion in monomials, okay? Where I'm combinatory, so I see more things if I have these objects, and you can extract more information from such an expansion here, okay? But from here to here, it really depends how your symmetric function is given. There's no magical way to go from here to here. Okay, so that's really what we did before, okay? We had a symmetric function, and we actually expanded it into combinatorial objects. So I'd say we're now that it actually comes, it's supposed to come from representation. We also had this Q, so in general, you can have gradings in your representations, and then you have a graded Frobenius characteristics, so just add parameters to actually record the different gradings that you can have, okay? So one parameter for each grading. Okay, so that's for specific representations. You like to do all of these things if you have a representation. So what are the representations in particular here? So let's be fast. So these are these generalized covariant spaces, let's say. So you have Sn acts on polynomials, as usual. It also acts on the exterior algebra, where you have now anti-commuting variables. Okay, so in both cases, the total degree is preserved, so you have a grading in each case. And then you can combine them by just doing tensor products of all of this with A copies of one, B copies of the other one. And then you will have you have a nice space. This one is fairly well understood. And it's also infinite dimensional. I want finite dimensional. And now what you do is taking the invariants and looking at the ones with a zero constant term, looking at the ideal that they generate, and then taking the co-invariance. So you actually quotient by this ideal here. And then in general, you get a finite dimensional space, which is this generalized co-invariant spaces. So I should say I haven't recorded a lot of history. There are a lot of people to cite, maybe, let's say, Bergeron, Garcia, Heyman to begin with, and many people, somewhere in this room, to cite. So if you want to know more, maybe there's Brendan Rhodes, who must be somewhere here, who wrote a chapter for an upcoming book about, let's say, the different things that have been constructed. Okay. So plus you have the gradings here, okay? I told you each piece here has a grading, so you would have an indeterminate for each head. Okay, so as I said, for 1, 0, 2, 0, it's our classical stuff. We'll go a bit more for small values of A and B, and what are actually the particular co-invariant spaces that are related to our symmetric function. Okay, so this would be A and B are basically 1 or 2 in what's coming. So Mike Zabrowski had conjectured, yep. No, not the invariant. I'm talking, they are not, no, sorry. I don't know. Maybe I missed, no, there's no plus here. That's the tensor product here, so there's no invariance. And then No. Unless, no. It's just the total big space, and then you quotient by the T. Maybe my notations are not. They're not classical notations at all. I'll just define my own notation. Okay. I mean, there may be mistakes, but I don't think this one is, clearly. Especially if affiliation. But anyway, just attributing the different things. But I think Mike Zabrowski conjecture that for this 2-1 case, so 2 sets of commuting variables, 1 set of anti-commuting, and it should be equal to this, the Frobenius characteristic, the graded one, should be equal to this thing. So delta prime is certain operator that I don't want to talk about, and there are Q and T hidden in this delta prime, okay? And then this was generalized more recently by my collaborators with Michele D'Addario to the 2-2 case, okay? So now you have 2 sets of commuting, 2 sets of anti-commuting. And then for this, they had to define these new operators, the theta operators. And then you get this complicated thing here. There's also a nabla, sorry. It's also another operator hidden in there. And this is supposed to, this is a symmetric function with like 2 parameters. 4 parameters, sorry, U, V, Q, and T. And this is conjecturally the graded Frobenius of this. But you probably don't remember, but this is exactly, if you take T equals 0, this is the definition of my symmetric function OTQ and yeah. So it means that now if you take this and basically you put T equals 0 there, so that you forget about the, sorry, T equals 0. Then this is precisely the OTQ and KL, and this is what I told you like at the beginning. This is conjecturally the graded Frobenius of this co-invariant space with 1 set of commuting variables and 2 sets of anti-commuting variables. Sorry? Yeah, it's R22, but then I specialized. So this one specialized at T equals 0. So it brings you down from 2 set of commuting variables to 1. Okay. Okay, so this is for the, so these are conjectures for a reason. They're hard stuff, so people don't know. So they're going from the, trying to find the graded Frobenius characteristic is hard in general. So it was known, for instance, 2-0, that's the work of Heyman, that's celebrated. But in general, it's hard, so people do the second part, which is going from the symmetric functions to, I mean, I do actually, to the combinatorics, to find a combinatorial expansion. So, so for instance, if you take 2-0, that's the famous shuffle theorem, okay, that was proven not too long ago. And if you take the 2-1 case, so this is really what occurs there. The combinatorial expansion is There were two different ones that were conjectures. So there's so-called delta conjectures are precisely these two ways to express this symmetric function combinatorially. Okay, it's about some labeled disk path with some markings. I'll show them briefly in the next slide. And there's a rise version and a valley version. So this one is proved. This one is not proved because combinatorics are more complicated. So skip this, but this is what you sum over. So these are the labeled disk paths that you may have seen in many talks. And you have different ways to label the rises. If you just label with rises, you have this. If you just label with valleys, you have this. But you can also do both. So there's also a notion of area that I define here. The denv I don't define. But you can. So another conjecture is that you can actually take both the decorations at the same time, having both the rise and valley conjecture merge into one. But here you don't really know what the Q is supposed to be. But still, it's conjecture that this would be this would still work. You can take both decorations and still have a combinatorial expansion at Q equals 1. And what people in this area really want is to find what is the statistic on Q to actually conjecture the full combinatorial expansions for with 4 parameters. Okay. Let me speed. So basically, in our work, we can. If you now specialize these two, so it's a bit complicated because I still keep specializing and extending. But if you specialize this to t equals 0, it tells you that smear NKL should be in bijection with an area 0 path. And we have a bijection like this. So it's very combinatorial. Basically, you show once again that it satisfies the same recursion. So I have different ways. We have 4 different ways corresponding to the 4 binomial coefficients that you had. And not only this, but we can put in the Q. So we had this mid inversion on Smirnov. We can transport it to the path, but this doesn't work. So we have to modify it a little bit so that it specializes nicely to the delta conjectures. That's the key. That you want to, if you want to specialize to the rise or valley conjecture, you want to find exactly the same dim so that you have a unified delta conjecture. So we can do this in the simpler case where t equals 0. So I play a lot with Q and T. And so that's what we call the unified delta theorem at t equals 0, is this, this particular statement. And I'm stopping here. Thank you.
Okay, questions for Philippe?
So you mentioned for permutations, this is exactly Laguerre histories. I was wondering if you have an extension of Laguerre histories for Smirnov, segmented Smirnov words. Or if you've thought about that.
Not really, because no, I mean, I don't know. I want to say no, because like the fact that you go to the semi-standard case, depends what you call Laguerre histories. So basically this recurrence is some sort of histories. It's just one encoding of history, so maybe, but it wouldn't be this kind of nice Motzkin path with decorations, right? It would be some semi-standard way to do this, so I'm not direct.
Thank you.
Any other questions? Okay, let's thank Philippe again.